One of the future plans for humanity is to live on Mars at a time when Earth might no longer be a safe haven for life. Regardless of all the challenges ahead to achieve this goal, such as constructing dome-like structures, continuous oxygen production, environmental temperature control, shielding from hazardous solar radiation, and transferring equipment from Earth to Mars. Did you know that those who spend their remaining lives on Mars will have a shorter lifespan compared to other people who live on Earth? This phenomenon, which is created due to the difference in gravitational fields between the two planets, is called gravitational time dilation. But what is the exact meaning of that? There are two kinds of time dilation. The first one is the special relativity time dilation. This is a consequence of Albert Einstein's theory of special relativity. It states that as an object's velocity approaches the speed of light, time for that object passes more slowly relative to a stationary observer. Let's understand this phenomenon with a simple example. Imagine a narrow beam of light constantly reflecting between two parallel mirrors, and the round-trip time for this light beam is our reference unit of time. For instance, let's say each round trip of light between the mirrors takes 1 second. Now, if these two mirrors are placed on a moving train as shown in this movie, because the distance covered by the light is longer, it takes more time for a complete round trip to occur. Therefore, the 1 second measured by someone on the moving train is different from the 1 second measured by someone standing still, and time is experienced more slowly for the person in motion. It seems that we are chasing time, and the faster we move, the closer we get to the speed of time. And ultimately, if we have a speed equal to the speed of light, time stops. Another kind of time dilation is gravitational time dilation. This is a consequence of Einstein's theory of general relativity. It states that time passes more slowly in stronger gravitational fields. In other words, the closer an object is to a massive body like a planet or a star, the slower time flows for that object compared to a distant observer. This effect is why time passes differently on Earth's surface compared to high-altitude satellites, for example. In the interstellar movie, both types of time dilation have been mentioned.
One for you, one for me. When I'm up there in hypersleep, or traveling near the speed of light, or near a black hole, time's gonna change for me. It's gonna run more slowly. Now, when we get back, we're gonna compare.
Time will run differently for us?
Yeah. Maybe by the time I get back, we might even be the same age. You and me. What? Imagine that.
The gravitational time dilation arises due to the curvature of space-time. As we know, Einstein demonstrated that gravity isn't just a force. Rather, space bends near massive objects, causing bodies to be drawn towards them. Typically, the curvature of space is depicted in 2 dimensions in images for better understanding, but in reality, it must be considered in 3 dimensions, and its 3-dimensional arrangement is nearly like this. However, the thought-provoking point is that not only does space bend near massive bodies, but the time axis also becomes curved. Thus, the heavier the mass and the greater the space-time curvature, the longer time intervals become on the curved time axis. Consequently, time passes more slowly near massive objects compared to other places.
With one complication. The planet is much closer to Gargantua than we thought.
Gargantua. It's what we're calling them, the black hole. Miller's and Dr. Mann's planets both orbit it.
And Miller's is on the horizon?
Oh, it's a basketball around a hoop. Landing there takes us dangerously close, and a black hole that big has a huge gravitational pull.
Look, I could swing around that neutron star to decelerate.
No, it's not that. It's time. The gravity on that planet will slow our clock compared to Earth's drastically.
Oh, how bad?
Well, every hour we spend on that planet will be 7 years back on Earth.
Now, if we are near an extremely massive object like a black hole, the space-time curvature becomes so extreme that time intervals essentially tend towards infinity, and all times converge at a single point, as attempted to illustrate this phenomenon in the film Interstellar within a black hole. Since approaching a black hole is impossible, and due to its intense gravity, no light escapes from it, thereby withholding any information from it. Thus, this singularity in space-time remains an enigma. Both types of time dilation have been experimentally confirmed and are fundamental concepts in our understanding of the universe, especially in the realm of relativistic physics. I'm Dr. Shiva, and in the next video, I'm going to talk about the concept of wormhole and time travel.